Hello there, this is Coach Ikram, and welcome to this video on phase change diagrams. In this particular part of the unit, we're going to be using a lot of vocabulary to discuss the actions of phase change, including melting, freezing, evaporation, condensation, sublimation, and deposition. The important thing to note about phase changes themselves is that the temperature of the substance is not going to change when the phase is actually changing. So for example, if I take a pot of water and I bring it to a boil, the temperature changes while I bring the water to 100 degrees Celsius. But once I hit 100 degrees Celsius, that water is boiling and the temperature will not change from 100 degrees Celsius while that water is undergoing the phase change to a gas. So just to take some of the vocab, sublimation is going to be the change of a solid to a gas, and it's going to skip the liquid phase. Deposition is going to be the opposite. It's going to go from a gas right down to a solid, skipping the liquid phase. So for example, some examples of this are iodine, ice cube shrinkage, freeze drying, freezer burn, etc. So this is a handy diagram to kind of look visually at all of the different phase change actions that we've got here. So we'll primarily be sticking between water, vapor, liquid, water, and ice or frost for the following problems. But plasma, it is possible to change phases between water, vapor, and plasma. So some values that you're going to need to know for this part of the unit. The specific heat of water is going to be 4.184 joules over grams times degrees Celsius, or 1.0 calorie over grams times degrees Celsius. And this value can be found on your reference sheet. The specific heat of ice, so solid water, is going to be 2.03, and the specific heat of steam is going to be 2.06, and all of these can be found on your reference sheet. So the first phase change we're going to talk about is the molar heat of fusion. It's the heat required to melt a liquid. So the molar heat of fusion for water is 334 joules per grams, which is also a value you can find on your reference sheet. And the formula that we are going to be using to solve this is going to be Q equals M times the molar heat of fusion. Oh, right. Okay. Well, we're going to have to edit this. So grams. Make it mass. Let me check the other ones. So the first phase change that we're going to talk about is fusion. And the molar heat of fusion is going to be the heat required to melt a liquid. So the heat of fusion for water is going to be 334 joules over grams, which is a value that can be found on your reference sheet. And we're going to be solving using that equation, Q equals mass times the molar heat of fusion. And when we're solving for this, you note it looks a little bit like Q equals MCAT, but you'll notice there is no change in temperature. Because if you are melting a liquid, you're undergoing a phase change, and there is no change in temperature for that phase change. And if you're looking at an actual phase change diagram, we've got 0 degrees here, which is where ice would start to melt. So you've got below 0 degrees, you have ice. It's in the solid form. Once you hit this horizontal plateau right here, you are melting that ice into liquid, and then it becomes water right here. And note that the temperature does not change this entire time the ice is melting. Hence, you have no change in T in that Q equation. The opposite of that would be the molar heat of solidification. So heat is going to be released as 1 gram of liquid freezes. So if my heat of fusion is going to be equal to the negative of my heat of solidification, which should make sense because solidification would be if I'm going from water back to ice. And in order to do that, you have to release heat. And so it's going to be a negative value. So the next phase change that we're going to talk about is going to be the molar heat of vaporization. It's going to be the heat required to vaporize 1 mole of a liquid. And the value that we're going to use for that, for the change in heat of vaporization for water, is going to be 2,257 joules over grams. So in this case, our equation is going to be Q equals the mass times the heat of condensation or vaporization. And so this is going to be occurring, for example, at water, right here at 100 degrees. So we're going from liquid water to steam as it vaporizes, and note again that the temperature does not change. It stays constant at 100 degrees while that phase change is taking place. The opposite for that would be the heat of condensation. So again, just like our previous slide, this is going to be negative, because as you condense to a liquid and you go from steam to water, you have to release that heat. So when you're looking at the phase change diagram overall, the horizontal parts of the curve, so right here and right here, are going to be your state change or your phase change. The temperature is unchanged, but your potential energy is going to change. The sloped part of the curves, so here and here and here, those are going to be when your temperature is actually changing. That's at ice, water, and steam. And your temperature will change, and you'll have a change in kinetic and potential energy. So if I'm going to solve a problem using this particular graph and using these equations, it says how much heat in joules is needed to melt 150 grams of ice at 0 degrees Celsius. So if you are melting ice, remember there is no temperature change for this because you're undergoing a phase change. My equation is going to be Q equals the mass times my heat of fusion. And so Q value is going to be equal to 150.0 times my molar heat of fusion, which we said on the previous slide and on your reference sheet, is 334 joules per gram. And my Q value overall is going to be this value with 3 significant digits. So that is how much heat is required to melt 150 grams of ice. Another example of this, and I should read number 2 here. How much heat in joules is needed to heat the liquid water from the previous problem, which is 150 grams, to 20 degrees Celsius? So now we have melted the liquid, or melted the ice to a liquid, and now we're going to start at that point and we're going to heat that liquid water up. So in this case, we do have a temperature change because we're not undergoing a phase change. We're simply heating the water that we already have. So in this case, you're going to go back to our Q equals MC delta T. So Q value is going to be our mass times the C value for water, because we're at liquid water at this point, so it's 4.184. And my change in temperature, it doesn't give me an initial temperature. I have the final temperature here at 20.0 degrees Celsius. But remember, if I'm piggybacking off the previous problem, we melted that ice at 0 degrees, and now we're heating it up to 20 degrees. So it started at 0 degrees. So my final minus initial is going to be 20.0 minus 0. For my Q value, in order to heat this water up, it's going to be 126.00 joules with 3 significant digits. All right, this problem says how many joules are released when 36.0 grams of steam at 100 degrees Celsius condenses to water at 100 degrees Celsius and then cools to 50 degrees. So this is actually a 2-part problem. I'm doing 2 things here. I'm undergoing that phase change to go from steam to water, and then I'm going to cool that water down to 50 degrees. So I'm going to put this into 2 parts, part 1 and part 2. Part 1 is going to be my phase change. So for this particular problem, that's going to be Q equals molar mass, heat of condensation. Remember, there's no temperature change here. So my mass is going to be 36.0 grams. And my heat is going to be 2257 per the reference sheet. And then my Q value is going to be equal to, which rounds off to 3 significant digits, at 81300. Remember, heat is being released, so my Q value is going to be negative. Now, the second part of my problem, I'm cooling water from that 100 degrees down to 50 degrees, so this is just a Q equals MCAP problem. And we do have a temperature change here. So Q in this case is going to be equal to my mass, which is 36 grams. Remember, mass doesn't change. My C value for water is 4.184. And my change in T in this case is going to be 50 minus 100. Final minus initial, so we get negative 50 degrees. 0.0, sorry, ran out of room. So I'm going to go ahead and solve, and I get a negative, when I do significant figures, 3 significant digits, 7530 joules. Now I'm not completely done because I want to know my total amount of energy released, my joules released. So I'm going to add those two numbers together, part 1 and part 2, to get my total heat released in this particular scenario. And when I add these two together, I get my Q value is a negative. And there's no places after the decimal to follow the addition and subtraction significant figures rules. And that's how you do a 2-part problem. All right. That is the end of these notes. Make sure you take good notes and come to class with questions. Thanks.